Hello, and welcome to today's T&D World webinar titled Underground Substation for the Greater Cambridge Energy Program, sponsored by Power Delivery Intelligence Initiative in partnership with Eversource. I'm Jeff Postlewaite, Managing Editor for T&D World with Endeavor Business Media. We're glad you're all here, and just a few housekeeping notes at the top here. If you have any technical difficulties during today's session, submit to the questions window, and our technical experts will help you out. We recommend that you turn off any of your pop-up blockers or extensions in your browser, because those can sometimes cause some issues with the player. And we really do want to hear your questions during today's event. That's part of what makes so interesting is the interactivity. So you can submit your questions as soon as you think about them at any time. You don't have to wait for the Q&A to follow. Just type them in as they occur to you in the question window on the side of your screen and hit the submit button. And to refer a colleague to today's discussion or share it on social media or access the event resources, you can click on the icons on the left side rail of your screen. And please be aware that this one is going to be recorded and available on the T&D World website within the next day. We will email you when that's ready. And so with that out of the way, I just want to introduce Chris Arnieri, who is Manager of Substation Design Engineering, and Mike Beeler, who is National Spokesperson for the Power Delivery Intelligence Initiative. And I know they've got a lot to say to you, so I'll let them go ahead.
All right, Jeff, thank you very much. Appreciate it. And we'll advance to the next slide here, and we'll tell you what is the Power Delivery Intelligence Initiative. Basically, it's a group of contractors and consultants and equipment manufacturers and cable manufacturers that advocate for underground versus overhead. We want planners and engineers and data scientists like the ones we're going to meet today at Eversource Energy to evaluate underground and the total cost of ownership over the life of the asset. So today we're going to talk with Eversource Energy, and I'm going to introduce you to Chris here real quick. But this is the first webinar that we've done this year at Power Delivery Intelligence Initiative, and I think it's one of the most interesting projects that I've run into in a long time. It is a massive underground substation in the heart of downtown Boston. And I saw this project probably last summer, and I just said to my friends at Eversource, boy, we have got to let the industry know more about this. And I know Chris has been out there a little bit. Chris, a couple of words of welcome to you, just to say hello so they can hear your voice. Chris Arnieri from Eversource Energy, give us a quick hello.
Hi, guys. Thanks for having me.
Okay. So I really appreciate you, Chris. I know you've got a whole great deck of things to talk about. So again, I can think of one other underground substation domestically here in the United States, and that is in Anaheim. It's a 69 kV station, and it's been at Anaheim maybe for 30 or 35 years. So this is really state of the art. And when you think about undergrounding assets, we typically think of distribution lines and maybe a little bit of transmission as well at PDI squared, but a substation, and I think this is going to lead the way in the industry, Chris. So, Chris, enough of me, and let's hear what you've got to say about this most fascinating project.
Great. Thank you, Mike. Appreciate it. Definitely a quick thank you to PDI Squared, TD World, and Endeavor for all their hard work to make this webinar possible. And, one last thank you to Sean Flajagic, the Vice President of Engineering for Eversource, for bringing this opportunity to me. So with that said, here we're really to talk about the underground substation for the Greater Cambridge Energy Program. It's really the focal point of the substation, or of the program in and of itself. Really what we're looking through today is what I plan to talk about is, give a brief overview of the Greater Cambridge Energy Program, then dive right in to talk about how the transmission lines, substation connections are, how the distribution line substations connections are, to really pontificate on what Mike was alluding to, or the substation of the future, or what we're considering our first substation of future for Eversource. And then lastly, I'll be talking through a lot of the below grade substation systems that you really don't think about when you're doing traditional substations.
And Chris, I'll volunteer. I hope this is the substation of the future. I hope you set an example for many other utilities in America that think, especially ones that are trying to build substations on transmission lines in urban centers where they want to serve big data loads and such. This is a great idea. So I hope you are going to, provide that for other utilities across America and North America.
Hope so as well. So really, for the Greater Cambridge Energy Program, initially in 2014, we developed a need, and we had to come up with a solution to eliminate the electrical islanding served from a single shared substation that supplies this area. And then on top of it, with the way the area is getting redeveloped, and plus the political movement to move to electrification, we were seeing significant load growth opportunity. So we had started our property search. We were really fighting up against other developers looking to buy land to build, development. And really for us, it became a struggle. So we were very limited on the parcels that we as a company were able to procure. In 2017, we were able to identify, if you look at the image on the right, the orange kind of triangle looking thing. We were able to procure that land and get the rights to it. As we started doing our initial outreach, we had a major opposition from the local area and the city as well, considering the property was across from an elementary school and on the backside was single level of residential homes. So with that, we made a very quick response, engaged the community between the city of Cambridge, local community groups, and also started to talk to other developers as well. The city of Cambridge, they were able to make some land potentially available, which is shown in the green, weird looking shaped thing that you see below on the image on the right. And as you can just see, just the weird topology of that, there was no way we could build a station in there. And then we started talking with Boston Properties, which is now called BXP. They had a development planned for in the blue section in that image, which was currently a above grade parking garage that they were going to tear down and redevelop. And after long negotiation and talking with them, we decided to move the substation from the orange parcel that we owned over into the blue and co-develop. And really the trigger with the city of Cambridge was to start to look at the undergrounding efforts here and what it would take. And then with the whole program, and you'll see, should get this general feel from this, is that we really built this in conjunction, or designed this in conjunction with all of our partners, with BXP, all the neighborhood communities, the city of Cambridge, all the abutters to the parcel and whatnot, including not just at the substation, but also on the transmission lines and the distribution lines, and really to buy a full community engagement with this project. So as I mentioned before, the islanding effect of this area, in this image, you can see in the yellow circle, really this area is fed from 2 transmission lines. There are a couple of stations in between, but then eventually you get to one substation that's only fed by a single transmission line. So you can see in an event, if one is out on one line is out on service, and then you have an event on the other line, functionally you're making the entire yellow block black. Not a very good situation to be in. So the proposed solution here was to add a new substation, which is what we're calling 8025, and it's the below grade substation, but then to reconfigure it to bring 8 transmission lines. This is all at 115,000 volts into the substation and getting connection, so it's no longer a radial fed substation. The substation in general consists of 115,000 volt switchgear. It's in a 6-bay breaker and a half arrangement. There's, like I said, 8 transmission lines. There's 4 oil-filled power transformers to serve the increased distribution load, but also as well as the electrification of the area, including EV charging, et cetera.
Hey, Chris, a quick question. All that's your transmission system in downtown Boston and Cambridge, that's all underground to begin with anyway, right?
Mostly, yeah. It's all the transmission lines are all underground. Yes.
Yep.
Yeah, the substations are typically, up until this point, have been above grade.
Okay, thank you.
No problem. Yep, and then to support the distribution load, 6 sections of metal-clad switchgear on a main bus configuration, and then just to support power quality and voltage stabilization, we have 6 13,800 volt metal clad capacitor banks. So again, we're ultra sensitive to the way the area looked today. And with this development, we really wanted to make sure that what we were doing was going to blend into the area. So, a person that wasn't around during the construction, while they might know see the newness of the buildings, they wouldn't really think that it's very much different. So what we can see here in this video is the left is a residential tower, on the right is a commercial building, and then the substation kind of sandwiched in between. And this really kind of the idea is to show you the different cross sections, starting to show how we really were leveraging 3D design in here to make it all blend and get community buy-in. This video is even on our on the webpage for this as well. I think there's actually a better voiceover, but there is to kind of give a rough understanding of how the substation blends into this development. So when we look here, this is kind of giving a very closer view with the yellow on the right. The high-rise building is a residential tower. It is going to be the tallest tower in the city of Cambridge once they're done constructing it. The blue 2 buildings on the right side are commercial buildings for lab, office, what have you, all owned by BXP. And then you can see in the middle is the park space, or park/substation space. And this was a really big movement with hanging point with the city of Cambridge is we're going to bring in all these new residents. And then on top of it, we're going to give them a place to work. But where were they going to get some personal enjoyment, like for outdoor space, even though they're in a city, but trying to just do that for everyone. And that's where, working with BXP, we were able to look at below undergrounding. And then we started working with our other utility partners that do a lot of undergrounding. TEPCO is one in Japan. Then there's some in Vancouver area, and then the Toronto and Anaheim as well, and started gaining some confidence of a below grade substation. So as we start to talk about where the substation is, now we have to recognize that the substation is actually sandwiched between a residential and commercial, but also the property width is fairly limited. So when you start talking 8 transmission lines and all the distribution, we couldn't just pack all of that in one side and be able to get into the existing streets and have the room to keep the loading requirements. So we really split it to the transmission on functionally like south side, as you can see in the red here, and then the distribution of the north, which we'll talk about in a minute. But the trick here is we had to route these lines with enough spacing to keep their thermal capacities in acceptable form to be able to meet the loads of the station. Really, that meant we had to spread it out on the parcel, and then we had to, again, joint venture with BXP to route 3 of the transmission duct banks through the basement level of the high-rise building. We were lucky enough to get 2 of them just outside the building, but it definitely became problematic. So once we get the transmission lines in the station, and as you've kind of seen in the video before, the substation is very compact, right? And the transmission lines are cross-linked polyethylene cables. Some are multiple per phase, some are single per phase, depends on the circuit you're on. But there was no way we were going to be able to route that through the substation successfully while leaving space for the other gear. So as within the first 35 feet or so, we're passing the slurry wall of the station wall, we had to transition to gas insulated bus. And this picture here that we see in the different sections is showing the cross-linked polyethylene interfacing with the gas insulated bus. And then the yellow walls are actually, they're blast proof and they're removable. So in the event of a catastrophic failure on the transmission line, it wouldn't take out any other transmission duct bank grouping. But also, since they're removable, after the event, if we needed to re-pull, we could remove the wall to gain the additional space required to pull the cables back in to remake the connections to the gas insulated bus. So then we now need to talk about the distribution. This was a really heavy load on, engineering wise in the street, quite a significant amount of circuits. First thing we did is coming from the north side, and you can see in the red, the distribution circuits, we transitioned them into the closest point to the commercial building, and we put pulling vaults into that space. Since the commercial building had a below grade parking garage, we had to heavily work with BXP to figure out how to route distribution duct banks on the top ceiling of the topmost garage level. As you can see from this image, there's a lot of stuff going on between ramps and passages and clearances for cars, but we also needed to keep the thermal ratings down on the distribution duct banks to supply the appropriate amount of load. One of the problems that came in is we were stuck at an elevation that was pretty high to the surface because of the parking garage, but our metal clad switchgear is all bottom entry, and we couldn't sink the switchgear low enough to be able to accommodate a top entry. So as you can see in this image, as soon as those distribution circuits come in, we essentially 90-degree down and bend into the floor below the metal clad switchgear, and then route them back on themselves on racking systems to get them to the distribution feeder sections.
Chris, one of the things I think is so fascinating about this project is not just electrical engineering, it's structural engineering, it's geotechnical engineering, it's HVAC and how you're going to handle the airflow and such. And you did the thermal analysis for the soils with the opacity of the cables and such. Really interesting project. Here's the question for you, did you use consultants on this, or did you have a team of men and women within Eversource that did the heavy lift on the technical part, or how'd you handle it?
It was really a mix of both. We had a lot of internal folks, but some of the stuff is outside of our internal capabilities, but others it was, timing, and we really we had a true blended crew here of external experts as well as internal experts to develop all this stuff and route it appropriately and do the loading calcs and thermal capacities and everything. So, good question. Thank you.
When it's appropriate, comment a little bit too. You said you went to KEPCO in Japan. You went to other utilities like Anaheim Public Utilities and such, and maybe comment a little bit on how some of your team internally interfaced with them when it fits in the presentation.
Sure. Yeah, I mean, it might be, this next slide might be a good part. So after our conversations with TEPCO and, in Vancouver and up in Toronto and out in Anaheim, we really started to get an understanding of the stuff that you really have to look for when you're talking about a below grade substation. And that's where we really made this pivotal switch. You've already gotten a little bit of a taste of the 3D, but that was when we made a full design decision, because we had never designed a substation in full 3D before as 3D modeling. And really, those conversations were mostly, presentations and different meetings, kind of getting an understanding of how they maintain, operate. We had our operation folks on those calls. We had our engineers on those calls, and really kind of building that experience that we just didn't have before we started this project. And that's really, I think TEPCO was the biggest one of saying, like, there's no way you should not be doing this in 3D. And, we went that way, and, really it proved itself as weight in gold. And that's kind of here what I'm trying to showcase is the technology utilization. So we were able to increase our design accuracy and efficiencies with here, because not only were we able to share our model with like our partners BXP, but we're able to share it with our manufacturers for like the GIS, the transformers, the metal clad switchgear, all our duct bank, like our bus ducts and things like that. And each group was able to add to their pieces of the models, and we were clearly able to see a clash very quickly and be able to work very smoothly. Within a week or two, we were able to resolve whatever that clashing issue was with whatever agency was working in that 3D model environment. If you think about it in a 2D, especially something of this size, one modification could potentially impact like 200 drawings in 2D, right? Whether it be in elevation or in plan, where in the model, you just update it, your cuts are already pre-established. So if you want those 2D, you can just hit a button and wait a few minutes and you're going to get the PDF 2D versions of your drawings that you need. So really incredibly efficiency by going to the 3D model here. Part of the images that I have.
I'm a huge fan of 3D. I'll just interject that. And I think a lot of manufacturers are using 3D and they have been using 3D for a long time. But the cool thing that you guys did at Eversource was this is a huge high profile project. And for the first time you used 3D. So credit to you, Chris, and your team, and to Asim and others for saying, okay, it's a gutsy move to go and do 3D on a project like this. It's good job.
Thank you. Yeah, and that's really what I'm trying to showcase here in the images is you can see the cuts on the substation section view on the upper right. You see an easy cut of half of the station, and you can see the duct banks, ventilation, you name it, everything's in there. And then on the bottom side, if you wanted a odd cut, like that is actually like an angled cut to see whatever piece of equipment or cable routing you might be looking, you can just cut it pretty instantaneously. And the point of the animation, that is actually a video file of the 3D model and me cross-sectioning the entire station. You can see it's basically a click of a mouse and you just start pulling down. So within seconds, you can be hatching and slashing this thing however you really want. But we weren't done there, right? We use this model to sit down with our operational folks and maintenance people to go through this, to do a virtual walkthrough of this substation, to gain their confidence to not just operate, but also maintain the station for 40 plus years, right? Which is huge because now they can actually see clearly what it is, the space they have, and the understanding of how to access different areas and get different pieces going through in and out. And then we decided, we had the 3D model, let's do a little bit more. And what we did, the final 3D design is tied to the project schedule. So like all the equipment installs and everything else all has actual projections of when they're going to be completed. The 3D model is tied to that. And there are video things that don't quite work yet because we're not in full construction, but they're going to start to track the actuals on the schedule. And of course, we also tied that from the schedule to the cash flows. So as you see a transformer gets put in service, we will see that that's an actual cost versus the projection and the time frame moving in the future as we're continuing on the construction. So we had all this, but then there was still the question of how do you get the equipment under how you do it. We have many of these. I only am showcasing one, which is the large power transformer. You can see the crane dropping the transformer in, transformer getting down to the bottommost, and then our plan to utilize a rail system. The time working with a manufacturer, we may go with air pocket blankets or robotics, but as we get closer, we'll figure that out. But you can start to see if we were doing a rail system, we do have to do some transitions to rotate or move it into the final landing spot. And then also we have to, as you will see in a second here, with the transformer oil containment, we do have to consider in some additional bridging, which we're going to see here in a minute, just to help the riggers. And now we can start seeing new rails come in, transformer get dropped in, and then start to remove the rigging equipment. And then final last piece that we'll see here is the crane system that has to be, it's a temporary crane system. The crane basically stays there. We only have like one or two for the station, but that's where they can do their final assembly of the heavy lift of the transformer. So for the substation, we also had to consider like large equipment, but we don't want to open that large equipment hatch for every piece of equipment, just for other reasons, weather impacts, or just having a general pit all the way down to the bottom floor, or depending on what floor blockade is in. So we did have to consider access for smaller equipment where we have a freight elevator built in. And then here we can see the large truck showing up with a shipment. The plan is to have a spider crane that's always sitting at the station with a boom crane off the side of the garage entry gate, but that can do the smaller pieces that can fit in the freight elevator to bring it to whatever floor we need. Overview here is we can see where the distribution duct banks, which we already talked about, the transmission, but then we can start to get a better understanding of the 7 floors that Mike mentioned before, where we have the B0 level, B1. The mezzanine levels are functionally cable routing levels or gas insulated bus routing levels to get from one side of the station to the other and do that cleanly and accurately. And then finally our B5 level, which has all the heaviest pieces of equipment are all on the B5 level. So as I mentioned before, City of Cambridge really wanted, public space that's outdoors that would be on top of the substation. So this is another point where we were heavily involved with the BXP and City of Cambridge and all the communities in the area to help develop a space that was usable to the public, right? We didn't just want to pave the thing on top and just say, hey, public, here you go. So in the early throws, the main image that you can see here is the artist's drawings of what the space could be. Then there was a 3D rendering done shortly thereafter, which is shown on the bottom right. The final development of this thing is pretty close to a blend of both, where there is some grass space, but there's also some trees, but the trees are all kept in planter boxes. So they're going to be limited height growth and also prevent any damage to the roof of the substation. So there is that barrier between the substation and this park space as well. From there, then we had to start thinking mechanical protection systems, really building in. And this was, again, kind of things that we learned from our outreach to the other utilities that have these below grade substations. We did bring some of our own flavor for our own protection system or different mechanical protection systems as well. But we first started off with a blast overpressure, knowing that the transformers were going to be oil filled. TEPCO is a big fan of, or not big fan, but they do utilize gas insulated transformers. We looked at it. We've never used them before in the past. Physically, they didn't quite fit in the spaces that we had available for them. So we stuck with oil for that reason. But knowing that we went with oil, that's why we did a very intensive blast overpressure study on this. And we designed the walls and the access doors to withstand and reflect the blast and keep it contained to the vault room. When we started seeing the results of that, we realized that, well, we contained the blast successfully, but we can't guarantee that a personnel worker wouldn't be in the vault when that happened. Now they had appropriate emergency egresses, but just the height of the overpressure blast was a little nerve-wracking. So that's when we looked out to do a fast depressurizing system on the transformer. We partnered with TransProCo for a transformer protector that they offer. That system depressurizes the tank within milliseconds. It's essentially activated by the first dynamic pressure peak. And then the way it actually operates is it separates the gases from the oils of the transformer. And then it channels the flammable gases. And in this case, we actually channel it all the way back up to the topmost point of the exhaust shaft that we'll talk about in a little bit. And then last was our water mist fire protection system. This is a system that came to us a few years back, and we have successfully implemented this in outdoor stations. We've done it in a few indoor stations as well. It's a technology that we found from Marioff High Fog, what it's called, and it's basically a high pressure water mist system. What this does is there's a massive pump that takes a standard water line, like a 2-inch water line, and it builds pressure on that and comes out through these specialized high pressure nozzles that generate very fine mist droplets. Those mist droplets then hit the piece of equipment that you're trying to put the fire out on. That starts to wet the device, but they're also directly focused on where the fuel system is coming to deplete the oxygen or displace the oxygen to mitigate the fire. The huge advantage of this is it's like a tenth of the amount of water that's generated from a deluge system. So when you think about an indoor below grade substation with an oil containment, to minimize the amount of water that could be put into your oil containment, if your transformer did let go oil as well, we're less concerned about the water overflowing and spilling and causing like an oil slick on the main floor, because now we're generating very little water to put out the fire. And if the oil does, the oil truly with the water will stay contained into the transformer bay.
So, Chris, let me interject a quick question here, and I'll say that we have a lot of great questions coming in from the audience that we'll get to here shortly. But here's a question. Did you have any codes that you needed to comply with? This is very unique to our industry. I can't imagine that there'd be anything in the National Electric Safety Code, for example, but any kind of codes from other industries that maybe you said we should apply to this underground substation?
So really, because of the 7 levels, basically we were stuck into the building code, or the biggest one was the building code, and it was the building code on high-rise structures. As weird as that sounds, but it's the high-rise structures only concerns about the total height of the structure, and it doesn't matter whether you're going down below or up. So there was a lot of those type of codes that we did have to apply. We did, and I'll get into it a little bit, we did interact very well with the Cambridge City Fire as well. But then we also hired more experts on top of all of this to start to look at like general life safety and other things, which I will actually pontificate a bit more in a little bit.
Very good. Thank you.
So another big thing that we did have to look at is how do we cool and vent this whole thing? When you look at just the transformers and then the residual loads from the switchgear and everything else, and the fact that thermally you're surrounded by a blanket, right? By being this far below grade. Our calculations here were around somewhere just 6.3 million BTU per hour for the heat removal. That translates to about a 1.5 million cubic feet per minute airflow that's required to keep this thing at the operational levels for all the manufacturing plus personnel as well. In certain select spaces that we had, like technology, like control systems, IT technology for like network servers and racks like that, we did have to go to a point where we couldn't air cool the system, and we had to do dedicated HVAC on those rooms. Then once we kind of figured all that out, we also realized that we had to have a redundancy. And that's really, we couldn't afford, like whether the fan or exhaust or intake fan needed to come out of service for regular maintenance or it failed. We had to have a redundancy. So no matter what, we were always keeping the ability to hit that airflow or air volume that we needed to move. Approximately, the whole design is just shy of 100 intake and exhaust fans. So it is a massive amount of air ventilation. This is one that we did outsource to some of our partners that specialize in airflow and cooling and heating.
Well, see, it's a good thing too that you got with your operations and maintenance teams on this, because this is nothing that they'd ever done before. They didn't have to.
Right.
They didn't have to serve 100 different ventilation systems in a single substation.
No, this is new for them for this. Just definitely the volume. So kind of moving from the ventilation, right? Intake is pretty easy, right? We're just pulling air in. So really the only thing we were cognizant of was with those high CFMs, was just the pull of air when someone's near the intake structure. But due to the design of the intake, we were able to pull from a higher level that the general public or the residential tower didn't see any impacts. But the exhaust side was particularly an issue, because now anything for air particulates, yes, we have air filters and things, but all of that leaving, especially the heat, because the air filter does not block heat. right? We had to do a full computational fluid dynamics model of this area. In the upper right, what you see in that is actually the 3D computational model showing that exhaust stack blowing out the louvers of the exhaust tower. And as you can see, it's a pretty violent uh, plenum that's coming out. So when we did this model, we had to think about temperature and the plume mixing. For folks that aren't familiar, plume mixing is basically any of the particulates that could be, like oil smell, not oil itself, but like other things like that, that has a way of coming out past the filters and then blowing into the air. When you do this model, we also have to consider that we're in a city. Cities naturally have their own wind tunnels. So we had to do a whole analysis of identifying what the worst case wind or situation would be with how that would be, the wind itself would be pushing this heat in plenum. The models on the left side in the images below are graphing temperature. On the right is the plume mixing, is what I was talking about. So temperature wise, it's very controlled right before you start seeing a temperature drop. And it really drops to a normal temperature before you get to the commercial building on the left side. But the air dilution, the plume mixing, that one does get a bit messier, right? It starts to expand. The good news here through the ventilation and other things that we utilized, that it's less than a 1% air mixing when you get up to the topmost level of the commercial building. So this is 1% or less, like a person couldn't even actually distinguish between normal ambient air and one less than one. But we had more than just the buildings next to us. We also have to consider that it's a public park. And that's the two images on the bottom. On the left side is showing the heat coming out of the exhaust shaft, and the people is average 6 foot tall person. So as you can see, as they get close, right up close to the vent shaft, they might feel a few degree temperature difference between the ambient and, you know, this thing pushing, the substation pushing out air. But it would be very, very minimal, and you'd really have to be almost standing, leaning up against the exhaust shaft. Then with the air dilution mixer, this was more of the angle of the vents or the louvers on the vents and the exhaust. We were able to direct them up, and that really keeps people outside of the air plenum. So they're even less than 1%. They're like more like a 0.5% when they're standing here. But it was definitely a very highly complex model. We did have to reach out and outsource to this to have this whole thing designed. Or analyzed, so that way we could figure out how we had to do any adjustments to the design. And a lot of it was louver changing and utilizing different ventilation filters as well. So then this is the question that I get asked the most. Below grade substation, you have a water table of around 6.5 feet below the surface. Right, the substation itself is about 109 feet to the bottom most level. Everyone wants to know, what about water? So we thought that too, right? And when we looked at the flood resiliency study, partnered with City of Cambridge. They did a very good job of analyzing the whole area. They did this in 2017, then again in 22. Then we also brought on additional consultants that constantly kind of monitor this. And that's where we started to build our flood resiliency designs. For Eversource, what we did is we looked at the substation. The walls, the solar wall construction is pretty much watertight once they're in. We'll talk a little bit more on that in the next slide. But then the roof is completely waterproof, but really it comes down to, all right, we have the water building from a storm or hurricane, what have you. It was really looking at the elevation levels to keep any penetrations higher than the highest flood, anticipated flood levels. With that, basically, we put some safety margins of 5 to 6 feet. elevated from the top of the grade, and then we were looking to achieve a 2-foot freeboard before any penetration that's dropping down into the substation. So then this is where, with the slurry wall technology, they essentially put the slurry walls in first, but then they got to start digging the soil out. Well, they capture water when they do this. So as they start to dig, they're going to have water in here. So they're going to start to pump it out. And every level, they're utilizing a top-down construction where they put the roof on, have some glory holes, but then they start doing the next level down. They do half the side of the floor. They start digging down on the other side of the floor. Once they get to the appropriate depth, they can start. But throughout this entire process, they're constantly pumping water, making sure it's dry, checking the slurry wall for dryness, for making sure there's no water penetrating through the walls. And basically, if they run into it, they're putting high pressure grout, fix the slurry wall so that way more water isn't coming in. In addition to all this, once we're done, we have a redundant sump pump system here. So as water could penetrate, however it may, we also have a redundant sump pump system that would pump the water back out if it did start to breach the station. One of the other technologies that we also recognized was on the transmission and distribution lines. As they come into the station, that's a penetration through the slurry wall, which is by definition waterproof. But our bigger concern was when you think of the transmission line, you're going to get so far and then you're going to have a manhole, and most manholes just let water come in. So what we partnered with was a company called Roxtech. They create a conduit cable seal device, which you can see in the image on the lower right. It's a rubber membrane that rolls around the cables to keep the cable integrity, but then it's a pressurized system that basically blocks anything coming through the conduit. Not only do we have these at the slurry wall, we're also going to have them at the first manhole out. So the intent is to keep the pressure volume down in those conduits leading up to the substation, but let the water be in the manhole. Why am I getting pushed to audience? So last measure that we're looking to roll out is what I'm showing here is the flood resiliency. For the flood resiliency is basically these plastic barriers. They're deployable flood control system. The plan is that we would have these pre-staged at a service center close to us. As we see a potential weather event that we think could impact this substation, the plan would be to roll out these deployable flood control systems around our most sensitive areas of the substation to really give that extra blocking capability in the case of event of a major hurricane or whatnot. All right. So now we've kind of talked a lot about the flood, and now it's really kind of building, Mike, where we were talking before on life safety and things like that. And this was one that we were very ultra sensitive to. Right, we have people working in there. Granted, all of our stations are manned, but we don't know when a person could be doing a breaker overhaul and whatnot. So we wanted to absolutely lockstep and keep this thing safe. First biggest thing, it was the emergency generator for this. So that emergency generator is sized to run the entire station. So in the event we lost our own station service power, that generator would fire up, and then the station will be fully self-sufficient off that generator for station service. With that, as I kind of alluded to, we have multiple fire protection systems, right, between the water mist system for the transformers. We have standard deluge throughout, all access ways, but then in some of the high electronic sensitive areas, we do use a Novik or a C2FN systems. Some of the GIS also contains C4FN. That's really in the gas insulated bus. The breakers are still SF6, so all oxygen depleting chemicals. So we do have a full oxygen depletion system throughout the entire facility. And then the biggest life safety one is the designed egress plan. It sounds simple, but like with dealing with a 7-floor thing with no windows, it was very complicated and actually forced equipment to change the design to be able to accommodate for those appropriate egresses.
I imagine your
We
crew training for this is really, really unique, and you probably only have a handful of substation crews that can actually go in here because you've got to have all the training to
well,
learn how
the
to
goal
operate
is to
safely.
train all of them. Yeah, I mean the goal is to train all of them. So
Oh, really?
yeah,
Okay.
yeah, anyone that goes into substations, the plan is to train everybody. Now, granted, there's got to, like you said, there will be a select few at first because we can't just train everyone all in one day. But you're right, it's going to be a very extensive training program. You know, one of the other parts too is when you get into the ventilation shafts or corridors, like you can see in the upper top right image. There is an emergency egress plan through some of those, but they're motor ventilation motors in there. So if all of them are running at full tilt, we're going to need hearing protection. But if they're in there and need to escape, they should already be wearing their hearing protection, right? They have to enter with that. You know, the other part we leveraged here is we really got a very close relationship, and they worked incredibly well with me. I can't, or not just me, but the entire team was Cambridge City Fire. We partnered with them. They were full born in helping us. They gave us more info than we could possibly know what to do with, but we still worked together and we came up with a great system, looking at the fire hardening, the rescue assessments. You know, even with them, we have a full fire control room on the top level that they can access in a case of an event, either we or them, to help mitigate any of this. And then we had to make sure we achieved, you know, kind of from a question earlier, you know, building for the building permit, we had to make sure we had full code compliance, and they were monumental to helping us gain that and working through those issues and processes. So building on the fire protection, life safety, a lot of the biggest simulations that we had to do was we had to do heat profiles throughout the entire station. We had to look at the velocity vectors, or like really the movement of air, even without, you know, through the ventilation or not in the ventilation. And then as well as once you have a fire, the smoke movement, how is it going to move within the sub, but also how do you get it out of the sub so people can start doing the repairs. And then lastly, the structural integrity. So assuming where fires are and looking at the main structural core members of the building, how do we best protect them? And those are also incorporated from this dynamics simulation. We were able to identify those. Like I was mentioning before, the explosion analysis, we did that on the transformers, but we did that on everything else. So we really had to watch explosion pressures, figure out where the points are. If there was an area that needed to be beefed up, we did. And then the same thing with the full ventilation assessment to make sure it could actually move the smoke or gas vapor mixes appropriately and get them out of the building to make it safe for any worker that may be in there or may be going in there to fix the ultimate problem.
The complexity of this is absolutely fascinating, Chris. Go ahead and last thought before we transition to Q&A.
So this is, I mean, this is really, I mean, the complexity of the station is absolutely incredible, right? And as you can see, this is probably only dipping the toe of your into something like this. And, you know, we really did have to truly leverage all of our consultants, all of our, you know, any technology available to really pull this all together. And, you know, it was absolutely incredible. I couldn't believe how many different things that I had to learn about, like air dispersion and things like that. Like, you know, the team on all of Greater Cambridge, they probably all in some way touched this substation. You know, and I definitely want to say thank you to all of them for their dedication and efforts, you know, whether it be legal, outreach, engineering, our vendors, you know, from manufacturing and engineering, and our data scientists that we had to pull into this. I mean, without their help, we would have absolutely never got to the point that we are. And then, you know, lastly for me is just thank you for the audience for attending today.
Well, we got some great questions from the audience here, and I'd say I do want to talk about cost. And I guess I'm going to introduce the questions with what kind of contractor did you use? And I'm thinking about safety during construction as well when I ask this question. Obviously, you got safety once you're operating and maintaining the station, but safety during construction, what kind of contractor did you find? Did you go to like a traditional, substation contractor? Certainly you needed to get somebody that could do something even more significant.
Yeah, so really this was part of the BXP partnership. So one of the biggest things is BXP has done many below grade parking garages. And some of them rival this depth, some exceed it. And they had the contractor connections between their internal engineering folks, but also their contractors that specialize in slurry wall construction and below grade. So we heavily leverage that and utilize the same. So the partnership here is BXP is helping. They are building the core shell is what I'm calling, which is basically the slurry wall and all the main floors. At some point when they're finished with that, they're going to turn the whole structure over to us to start to populate, fit, and fill.
Okay. Let's go through these. I'm going to take these questions kind of in the order that they came in, so we're going to kind of go in reverse order of the webinar. What were the trials and tribulations in pulling the cables into the duct banks? The number of cable joints increased to accommodate the bends and such? How the cable pulling go? You're not there yet, but you've done the design.
We're not. Yeah, we've done the design. Again, we do have a 3D animation model. So one of the things we did have to break, which is kind of breaking normal convention. Normally, you want to pull from the station out, right, for all this. Due to the compactness and just the sheer size of the transmission cables, we couldn't do that. So we're actually pulling the opposite way. We're pulling from the first manhole into the substation to allow for that. The distribution circuits are the same way. We're setting up the cable reels in those cable pulling the cable routing vaults on the outside of the commercial building. And then we're pulling into the substation, which is kind of breaking convention. You normally do it the other way around, right? You want to feed the cable in the substation, but unfortunately, due to the space and to get a tugger and all that other stuff, it was easier to put a mounted cable puller into those cable areas.
Okay. You answered this, but it's worth repeating. At what point did you engage the community? What was the process like?
So we engaged them really when we bought the first parcel across from the school. And there was a very anti position from that. So from there, when we saw how adamant people were not here, that's where we kept them pretty notified until we started to settle with an agreement with BXP. And then even then, we continued outreach meetings. It was pretty regular basis. They were doing about one a month for a while, and then they kind of stepped it down to like one every other month type of thing. And then they would have special events, especially when they were looking for community input for like the park plaza, right? So it was very specialized. It was a lot of outreach, a lot of hours.
Yeah, early and often. Here's another great question. This is, have you considered, and I know you mentioned it, but how to remove or replace equipment that may fail in the future? Is that's your elevator process, right?
Yeah, and that's really, we leverage it with the 3D model of putting it in, but what I didn't show in the presentation, just for limited time and whatnot, we also show it coming out. Probably the most difficult one is the gas insulated bus, because we have sections of that gas insulated bus that we had to be very particular with the design to make sure we were allowing for space for a section of that bus to be pulled out and then come back and be replaced while all the other bus is there. So we did look at that, and we also leverage a 3D model to determine that.
Okay. Battery system and protection system is absolutely key in this system. Is there adequate separation, redundancy, as well as venting for the stationary battery system? I would imagine batteries are still flooded lead acid and not lithium ion.
Correct. They're still flooded lead acid. But what we did with the battery rooms within the substation, and didn't really go through the nitty-gritty, but they're separated by like either side of the substation. So there's like a battery room, a whole bunch of other stuff, another battery room. So we purposely kept them completely isolated from themselves. The ventilation's the same thing with their just for the nitrogen storage or nitrogen buildup that could happen. Those rooms are fully ventilated. Any nitrogen that builds up on the ceiling is going to get pulled and sucked from the ventilation system.
Okay. So here's the last question, and this is actually the question I want to talk about is cost. What's the cost difference between the underground substation versus a comparable air-insulated switching station that's above ground?
So this one's a little tough because, like, if you try to compare it to like your traditional like air station, right? You really kind of have to match technology for technology. Typically if you're doing an air insulated substation, that just air insulated to gas insulated is going to have a very big cost delta, right? So when we were like assessing it, we were looking at it from, if I had to build a station this compact as a high-rise building versus a below grade, the below grade was more expensive, but it wasn't like the order. I mean, it was like a delta of about like 60 to 70 million dollars difference for the below grading versus a high rise structure. So it's tough to compare it apple to apple here on that, because especially you go from gas insulated switchgear and you move to a dead tank breaker, right? The cost of the two don't even compare,
Right. Yeah, I think the O&M cost over the next 40, 50 years of the life of the asset is different as well. And I think that's some of the things that engineers and planners need to take into account. In this particular case, though, when you're routing permit sensitive projects in heavy urban areas, it's like you can build a project underground or you can not build a project. It's like you want to build it, you will put it where we don't have to look at it. And I think we'll see more and more of that in the industry to come. And I'm thinking, Chris, Arnieri, I think that the more people are going to reach out and talk to Eversource Energy and some of the team that you put together, some of the contractor and consultant team that you put together on this, because I think they're going to look at it and say, we need to do that in our major urban area as well. Let me give you a minute or two to give some final concluding remarks. We're at the top of the hour and before we wrap up. So, Chris, that was really, really interesting. Really appreciate it. What are your final thoughts?
Yeah, I mean, really, anywhere we're talking about condensed urban development, it really comes to this mindset of now as a utility, right? We're all kind of struggling. Like we have that initial automatic thing of we have a responsibility to the rate base. So cost is kind of a problem, right? And then when you get into urban areas, when you have virgin land or a piece of a parcel that may have a small building on it, right? Developers are also looking at that parcel as profit, right? So they're okay with paying more for these parcels that might be perfect for an electrical substation because you need it. But because of our obligation to the rate base, we can't compete with them on that land acquisition. So just to be looking at it, it really boils down to like putting us in a corner spot that's even smaller. If we start to below grade it, yes, we're paying more cost for things, but the other benefits is now you're getting the cities on your side because now you're giving a betterment to the area, right? The city. Now they have a new park that they may not have, or maybe you choose to put like up in Toronto, they did a museum on top of their below grade substation. So, there's opportunities there to increase betterment, but also there's opportunities to partner with a developer, like in this case, where the developer had something, they're willing to work with us. And to do that with them, we were able to achieve some common cost betterments so we could continue to use the same contractors that BXP were using. So there's no more in and out charge, right? It was minimized. So, this is definitely like absolutely incredible. Really, if anyone's looking to do this, it's you really want to focus. There's a lot of new systems that you really have to look at to make sure just the safety, reliability of all the equipment. And, it's an absolutely amazing project to be a part of.
It really is, and I'm putting your email address up there, Chris, so that people can email you with their thoughts on it. We're at the top of the hour. Just fascinating presentation. I think you're going to hear more about that in the industry in the months to come. Perhaps something in T&D World Magazine, perhaps something at T&D Live next September in Phoenix. So, hey, on behalf of Chris Arnieri at Eversource Energy. Thank you very much, Chris, and on behalf of the Power Delivery Intelligence Initiative and all of its members, we thank you very much for listening today. Jeff, I will hand it back to you, and thank you very much.
Yes, thank you. Thanks to Chris and Mike. That is all the time we have for today. If there's any questions that we didn't have time to answer, we can get back to you on those via email, but that is all. On behalf of T&D World, thanks again to our presenters and to PDI Squared to help us deliver it to you, and for Eversource for sponsoring the webinar, and for all of you, of course, for joining. I hope you have a great rest of your day.